Hi everyone. Today we're going to be continuing our notes in 3.2 using zeros to write polynomials. Today we're also going to talk about complex roots. I want to start off with the review that the imaginary unit I is just equal to the square root of -1. So anytime that we have the square root of a negative number, we can represent that using the imaginary unit I. So for example, 5i is also written as 5 times the square root of -1. So now I want to just rewrite each of these expressions using the imaginary unit. So here we have the square root of -9. This is equal to 3i. The square root of -98, well, I know that this has a factor of 49 times 2, so this would be equal to -1. The square root of -1 times 49 times 2. And so that tells me that I can pull out that -1 and that 49 out of the radical, and we get 7i root 2. In number 3, we have the square root of -4. This is equal to 2i. The square root of -125, well, we can pull out a factor of 25 here. And so we get 5 and that -1, so 5i root 5. Number 5, here we have the square root of -512. I know that 512 is equal to 256 times 2, and I know that 256 is a perfect square. So this is equal to 16i root 2. 4 plus and minus the square root of -12 over 2. First thing, I notice that we can simplify that square root. So we get 4 plus or minus 2i root 3. And this is all over 2. And then we can cancel out that factor of 2. So we get 2 plus or minus I root 3. Number 7, I can simplify that square root of -18. So we get 9 plus or minus 3i root 2 all over 12. We can cancel out a factor of 3. So we get 3 plus or minus I root 2 all over 4. And finally, we have that square root of -22. This here, there's no perfect square factors of 22, so we can just pull out that I. So we get -1 plus or minus I root 22 all over 2. Okay? So what is a complex number? A complex number is any number represented in the form, so a number in the form a plus bi, where a and b are real numbers. So like that number b is a real number coefficient, where a is the real component and then b is the imaginary component. Okay? We can represent these on the complex number plane, which is different from the plane that we're used to. We're used to the real number plane, which is where each of the axes are axes of the real numbers. Here on the complex plane, we have that the horizontal axis is the real axis, and then the vertical axis is the imaginary axis. So we can plot these points, the complex numbers, on the complex plane, looking at the real component and the imaginary component. So 2 plus 3i, we would go to the right 2 on the real plane, and then up 3 on the imaginary plane. And so this point here in quadrant 1 on the complex plane would be 2 plus 3i. 4 minus 5i, we're going to go to the right 4 and down 5. And so this would be the point 4 minus 5i on the complex plane. Okay, so number 10, solve the following equation, quadratic equation, and express your answer as a complex number in the form a plus bi. We're going to use the inspired to check our answers. So I notice that this quadratic here, we can't factor this quadratic. There are no numbers that would multiply to the product of 4 and 1 that would add to -3. Okay, so we can't factor this. So we're going to use the quadratic formula to solve this. As a reminder, the quadratic formula is -b plus or minus the square root b squared minus 4ac all over 2a, where a is the coefficient of the quadratic term, b is the coefficient for the linear term, and c is the constant term. So we have this is equal to 3 plus or minus the square root of b squared, so that would be negative 3 squared, or 9, minus 4 times 1, all over 2 times 4. So this would be equal to 3 plus or minus the square root of, we have 9 minus 16 is negative 7, all over 8. So this would be equal to 3 plus or minus I root 7, all over 8. The square root of 7 cannot be reduced, or simplified, I should say. So this is our final reduced solution here. All right. So let's go ahead and check our answers. I'm going to take this and put it into our calculator. So in your Inspire, go ahead and hit Add Calculator. We're going to use the C-Solve feature so you can type it out. And then plugging in the equation for x squared minus 3x plus 1 equals 0. And then comma, we're going to use x. So we're solving this equation for the variable x. I'm going to hit Enter. We see that we have 3 plus root 7 times I all over 8. And we have 3 minus root 7i all over 8. And so we verified our solution here. All right. Go ahead and flip the page. Now I want to talk about the complex and irrational conjugate factors of polynomial functions. So non-rational roots in polynomials with rational coefficients will always come in conjugate pairs. We can write these factors to these conjugate pairs and multiply to create the irreducible quadratic factors. Okay? So what does all this mean? This means that if you have the complex number 2 minus I is a root, then the complex conjugate 2 plus I is also a root. Okay? Similarly, if you have, I'm going to say if, say, a plus the square root of b, where b is an irrational number, the square root of b is an irrational number. So if this is a root, then the irrational conjugate is also a root. So then a minus the square root of b is a root. Okay? So these complex roots and these irrational conjugate roots always come in pairs. Okay? So if you have one, you have the other automatically. So let's try a few examples. Example 1, write a fourth degree polynomial that has roots at 2 and at 4 minus I, where one of the roots has multiplicity 2. Leave your answer as a linear or irreducible quadratic factor. Okay, so we know that this is fourth degree. We also know that we have a root at x equals 2. We've got another root at x equals 4 minus I. Okay? Well, because of this, we've got a complex root. I know that its complex conjugate, 4 plus I, is also a root. Because each of these complex roots have multiplicity 1, and we know that one of the roots has multiplicity 2, that tells me that the root at x equals 2 has multiplicity 2. Okay? So already we can start to write out the factorization, or a possible factorization. F of x equals the quantity x minus 2 squared. We're going to write out that other factor as well, but we need to use our zeros, our complex roots, to find that irreducible quadratic factor. So I know that we have x is equal to 4 plus or minus I, right? So if I wanted to get this equal to 0, remember, where this irreducible quadratic factor equals 0 is where we have these roots, or where we have these solutions for x-intercepts. So therefore, I'm going to try to get this equal to 0. So first things first, I'm going to subtract 4 from both sides. So we have x minus 4 is equal to plus or minus I. I'm going to get rid of that I by squaring both sides, and we get the quantity x minus 4 squared is equal to the square of I, which is negative 1. Remember, I is equal to the square root of negative 1, so therefore I squared is equal to negative 1. Okay, we're going to expand this binomial squared, so we get x squared minus 8x plus 16, and that's equal to negative 1. And then adding 1 to both sides, we get x squared minus 8x plus 17 equals 0. And so this right here is our irreducible quadratic factor, so that's going to be the other factor that we plug in to our function. So x squared minus 8x plus 17. Okay, So this is a possible factorization given the criteria above. All right, example 2, write a third degree polynomial that has roots at 0 and 1 minus the square root of 2. All right, so here we have x equals 0 is a root, and then we have x equals 1 minus the square root of 2. So that tells me that the irrational conjugate is also a root, so x equals 1 plus the square root of 2. And so then we can already write, I'm going to write g of x is equal to, here we have x, so that's one factor, that's for the root at 0. And then for the other root, I'm just going to write this off to the side here. We have x is equal to 1 plus or minus the square root of 2. And then again, setting this equal to, or getting this equal to 0, we're going to subtract 1 from both sides. So we get x minus 1 is equal to plus or minus the square root of 2. And then squaring both sides, we get x minus 1, the quantity squared, is equal to 2. We expand this binomial squared, so x squared minus 2x plus 1. I actually don't need that parenthesis, is equal to 2. So we expanded that binomial. And then subtracting 2 from both sides, x squared minus 2x minus 1 is equal to 0. Okay. So then that would be our other factor here. So we have x squared minus 2x minus 1. So again, this is a possible factorization for example 2. All right, our last example for today, last couple examples here, give an equation of the graphs below. Okay, so I noticed that this function f on the left has a 0 at -2, 1, and 3. This is a cubic, so each of these zeros have multiplicity 1. And it also has the y-intercept of 3. Okay, so off to the side, I'm just going to write f of 0 is equal to 3, because that's our y-intercept. So in order to write the equation here, we have f of x is equal to a, and I'll come back to that in just a moment, times the quantity x plus 2 times the quantity x minus 1 times the quantity x minus 3. The reason why I included a is because we need to determine what's going on with the function vertically. Because we have a y-intercept, we can use that to find our vertical stretch or compression, our a value, that leading coefficient. Okay, so we're going to use our y-intercept in order to solve for a. So we know that f of 0 is equal to 3. So this must be equal to where x equals 0. So we're going to plug in 0 anywhere that we see x, and then we're going to solve for a. So we get 3 is equal to a times 2 times -1 times -3. And so then we get 3 is equal to, this would be 6a. So then a is equal to 1/2, 3 divided by 6. So then the equation for this polynomial is f of x equals 1/2 the quantity x plus 2 times the quantity x minus 1 times the quantity x minus 3. And so this is the equation for this polynomial. We got one more. G is a quintic polynomial. So I see we have zeros at -2, -1, and 1. And we have a y-intercept of 2. So I know f of 0 is equal to 2. I also know this is a quintic polynomial, or degree 5. And I see that we've got a couple of zeros, or a couple of roots, that bounce off the x-axis. So that tells me for the zeros at x equals 1 and -1, these must have multiplicity 2, or an even multiplicity. Okay, so a possible factorization would be f of x is equal to a times the quantity x plus 2 times the quantity x plus 1 squared times the quantity x minus 1 squared. Okay, plugging in our y-intercept, we get 2 is equal to a times the quantity 0 plus 2 times the quantity 0 plus 1 squared times the quantity 0 minus 1 squared. And so we get 2 is equal to a times 2 times 1 times 1. And so we get a then is equal to 1. A is equal to 1. Okay, so that tells us that our vertical stretch, there is none. So then, oops, I've been writing f. This is the function g. So I'm just going to change that real quick. So g of x, there we go. So then g of x is equal to 1, which we could write or we could choose not to. The times the quantity x plus 2 times the quantity x plus 1 squared times the quantity x minus 1 squared. And this is our equation for g. All right. So today we reviewed the imaginary unit, remember, is the square root of -1. We talked about complex zeros. Remember, complex zeros always come in pairs. So if you have a complex zero, its complex conjugate is also a zero. Likewise, the irrational conjugates come in pairs as well. Okay, so this is this rule right here. We talked about writing the equations given criteria and given a graph. So we're going to get a lot of practice on this. So we'll see you tomorrow. Have a great day, everybody. Goodbye.